Okay, so today we're going to talk about the Dirac delta function. Let's get started. So, the Dirac delta. So, the way that we can approach the Dirac delta function is with a limiting procedure. You'll see what I mean by that in a minute. So let's consider a function of the following form. So let me just draw a picture of it first. So we basically want to consider a function that takes zero values except for in between these 2 points, epsilon over 2 plus and minus. And in that region, it is constant and has a height of 1 over epsilon, okay? So this we might call delta, the superscript epsilon of x. And by the way, this is from Cohen-Tannoudji's notes, one of the appendices. Mathematically, we might write that this guy is equal to 1 over epsilon within and 0 otherwise. Okay. And what we would like to do is try to evaluate an integral of the form plus or minus infinity with respect to x, this delta function. This isn't the Dirac delta yet, but it's the precursor to, multiplied by some arbitrary smooth function f of x. So the Dirac delta function often appears under integral signs, and so that's how we'll approach this problem. And the basic idea is if I have some sort of function f of x that is pretty much smooth and continuous, then as long as I consider a very small region, for example, some very small window like that, then the argument is that the function doesn't change very much within this window in the limit that epsilon becomes very small. So the idea is that we're going to say that this thing here is approximately equal to whatever the value f happens to be right at 0. So that'll just come out, we'll just take that as a constant, and then we have to perform the rest of the integral, which is just now over the delta function. And again, this approximation we're making holds in the limit that epsilon is very small, where the function doesn't change much, so we just replace the value with not necessarily its average value, but the value in the middle here, in the hopes that it doesn't change very much in this window. And with this prescribed functional form, we can go ahead and evaluate this, and we get well, we might as well integrate instead from minus epsilon over 2 to epsilon over 2, because the delta function is 0 outside of that window, and within the window, it's just a constant function of 1 over epsilon. So we're just integrating a constant here, so we get f of 0 times a constant, so we'll pull out the 1 over epsilon first, and then this integral, we're just doing an integral dx of no argument, or well, an argument of 1, and so this is just evaluates to x, and then we evaluate at the limits. And I hope you can see that what we find is x at the upper bound minus x at the lower bound. And here we just get epsilon, so this is f of naught 1 over epsilon times epsilon, which is f of 0. So now this so the result of this integral is just the value of the function f evaluated at x equals 0, provided that epsilon is very small, a, so that we can make this approximation here. So what we've done is effectively, this result of this integral is plucked out the value of f at 0. And this function delta of epsilon was constructed in exactly this way, such that that factor of epsilon doesn't come into play. So in the limiting case, what happens? We would write, where I'll replace, because epsilon doesn't have come in, we can drop the superscript, and we just have that the integral of a function times a delta function gives the value of the function at x equals 0. Now, the idea behind this is, basically in the limit that epsilon goes to 0, if we consider the function we're looking at here, if I imagine, let's say, dividing epsilon in half, then the width of it shrinks. So we get some new function that's, only within this smaller window, but the height grows at the same rate. And so we can kind of imagine a procedure in which we are squishing and simultaneously heightening this delta epsilon function, and in the limit we get this very, very thin in width and very, very tall in height peak. And the limiting procedure is when we take that limit basically to 0 and the height to infinity. So this limit is done in such a way that the area of this region enclosed by the delta function is constant. And I mean, the way you could see that is if we just compute what the area is, right? The area is epsilon times 1 over epsilon. This is epsilon, the height's 1 over epsilon. So in the case where I send epsilon to epsilon over 2, then this becomes 1 over epsilon over 2. So the width shrinks, but the height grows to 1 over epsilon over 2, which is, again, just 1. So this limiting procedure preserves the area under the curve of the delta function. Okay, that's nice. So what we've seen is that when we compute this integral of a function times the delta function, we get the value at 0 of the function. But we can generalize this a little bit and, say for example we wanted the value of the function at some f of x naught, or maybe x naught's over here. Then what we would instead have to write is delta x minus x naught f of x. So this is sort of a generalization, or if you go this way, we're specifying that x naught is 0. But I can center this delta function anywhere I like. I could put it over here, and then, if I imagine I have some function passing through, take the limiting procedure, I get the value of the function at x naught, just like in this case. And mathematically, perhaps, we can try. So, if I were to just start here again, say we didn't know what this was to be equal to, we could just do a change of variable. Say x prime is x minus x naught, which gives dx prime is dx still, and rewriting that, it's x equals x prime plus x naught. So we get, there should be a dx here of course, in here. We get delta x prime f of x prime plus x naught dx prime, okay? And if we just refer to the original formula, we get some function times a delta function. The integral collapses and we get the value of the function when x prime is 0. So in this case, when x prime becomes 0, we just get f of 0 plus x naught, or f of x naught. Okay. So again, I just kind of want to drive this point home. So we have some smooth function f of x. So this might be helpful to have a picture to accompany this description. So we have some smooth function f of x, and we multiply it by delta of x, and I'll just draw the epsilon, so maybe so there's my delta function. So I multiply the two together, and you can kind of just imagine what's going to happen if I write the product out. So I'll just say this is f of x. If I multiply the two functions together, then anywhere where this delta function is 0, f of x will be 0. So we have 0 over here and 0 over here. And then inside, it's just the value of the function times 1 over epsilon. So it's going to have the same form, same shape. It's just scaled. So something like that. Right? So this would be f of x times delta of x. Okay. And then we consider the limiting procedure as epsilon goes to 0. So we can imagine that this shrinks in width but grows in height to preserve the area. And I'll show a few steps here, I guess, in that process. And this thing shoots off to infinity. And so what we would have is basically this window gets smaller and smaller. So we have this smaller one, and then finally, whatever this was, we just get, you can kind of see that as epsilon becomes smaller and smaller, we really do get very close to this constant function within that range. So I guess this is f of x for epsilon. 2f of x over epsilon, and so on. And we are just left with the value of the function in this procedure at 0. You can kind of imagine. Multiplied by some epsilon factor. So in this limit, delta shrinks in width. Grows in height. Preserving its area such that this integral is unity. Right? This was the function we constructed such that that was the case. And so the conclusion is that upon integrating, this plucks off, we could say, the value of f of x at x equals 0, or more generally x naught, but in this simpler case we are just considering x equals 0. And I might add that the limits plus or minus infinity will always work, but actually the limits only need to contain the width of the delta function. So if I only integrated from minus epsilon over 2 to epsilon over 2, because it's 0 outside anyways, I'm fine. So basically the bounds just have to contain the location of the delta function. But plus or minus infinity will work too. And as I mentioned before, we can move the spike around to pick off different values of x. So more generally, delta x minus x naught is a delta function centered here, say, if this is some x naught, times f of x gives f of x naught. And the last thing I'll mention for this part of the lecture is, I'll mention actually something else after. This is analogous to the Kronecker delta, which if you remember from last week when we had some sum over n for n integer, we were looking at things like c sub n delta n comma m, where this is the Kronecker delta, which takes a value of 0 when n and m are different, and 1 when n and m are equal. So it's very analogous to the Dirac delta. This gave us, right, it's 0, this thing is always 0 unless n happens to be equal to m, in which case it's 1. So this would just leave us with c sub m. And so I hope you can kind of see the analogy between these two things. I might call this f sub n to make it even more explicit. So you can kind of think about the Dirac delta function as the continuum version of the Kronecker delta function. And the last thing I will mention before moving on is that other distributions will work. So we looked at this square step thing, but there are other ways to define the delta function in the same sort of limiting procedure. So for example, a function like 1 over 2 epsilon e to the minus absolute value of x over epsilon, which looks something like this. Here when x is 0, this is 1, so we just get 1 over 2 epsilon at the peak. So in the limit, epsilon goes to 0, delta epsilon of x of this guy, this is the delta function. And you can kind of again imagine that now as I decrease epsilon, the width of this will shrink, but simultaneously the height will grow, and it'll approach kind of this spike, this perfect spike. And this is normalized such that we have that d epsilon of x is 1. these are how all of these are constructed. So that's one version. Another one we could do is, so this is one version, there's another version. So now we have kind of a Gaussian shape. But again, the same principle, we squish and we elongate. So epsilon shrinks, the width of the peak gets smaller and smaller, the height grows, and it approaches the delta function in the same limit. And just one more, this one's a little more interesting, I guess, sine x over epsilon over x. This is something called a sinc function, where you have sine of x over x of some kind, and this looks like something like that. And at the sinc of, when x is 0, this part actually just goes to 1. So this is 1 times 1 over pi, so over here it's 1 over pi. But again, shrink and extend, and these all approach the Dirac delta function. So there are many ways to get at the Dirac delta, and they all do kind of the same job. And so sometimes if you're doing like programming, and because this is a very discontinuous function which is not necessarily well suited for programming, you might use a Gaussian of some very small width compared to the scales of your problem to approximate the delta function. Okay.